In the last few years, there's been a series of developing insights in the relationship into different kinds of long-distance infrared phenomena relating to gravitational memory effects and the so-called source theorems in quantum field theory. I spoke about this in this room last year. I'm not going to try to review this whole story now, but I am going to discuss one self-contained corner of it. So the minute you say the word infrared phenomena to a quantum field theorist, the first thing that they think of are the so-called infrared divergences that are encountered in computations of Feynman diagrams, in all physical scattering processes, in quantum electrodynamics, in quantum dynamics, or in gravity. And the problem of the so-called ultraviolet divergences, which was solved by renormalization and Nobel Prize awarded to Feynman, Tominaga, and Schwinger, that is a separate problem. It also happens when you start to compute loop diagrams that you get infrared divergences. And this was first noticed in work of Bloch and Norsing in the 30s. People really did a very complicated problem, decades of work on it, thousands of papers, textbooks, so on and so forth. And finally, the problem came to some kind of closure in a very famous theorem of Kenosha, Lee, and Number in the early 60s. And what they said is, we don't want to compute the S matrix. We don't want to compute amplitudes. We only want to compute probabilities. And the reason that we only want to compute probabilities is that real detectors have a finite resolution, and very infrared photons or gravitons or whatever will escape their detector. So S matrices are unphysical. Only probabilities are real. And it was shown that there was great disagreement with the experiment, and this work was, I think, correctly greatly applauded throughout the particle theory community. And it's interesting that in marked contrast when 10 years later, when Stephen came along and said, we don't want to compute amplitudes, we only want to compute probabilities, the world went into an uproar and said that's completely outrageous, even though the same words had been accepted 10 years earlier in quantum electrodynamics. Now, these reasons for saying that you only want to compute probabilities and not amplitudes sound rather different. But I hope by the end of the talk, I'm going to circle around very soon, I hope by the end of the talk that you're going to see that they may actually be practically the same thing. So we've been discussing new ways of thinking about infrared structure in gauge theory and gravity. And so a natural question is, do these recent developments shed any light on this whole problem of infrared divergences in quantum electrodynamics and in quantum chromodynamics? And obviously the answer is yes, I would be talking about it. And this talk is going to be a compendium of different results from different papers, but the main collaborators are Dan Capas, Stephen Hawking, Malcolm Perry, Arnold Barrio, and Sasha Jagoido. Okay, so what I'm going to do is I'm going to in quantum gravity, and I'm going to rederive some rather I'm going to come to some conclusion about how to deal with the infrared divergences, which looks sort of amazing and new and remarkable, except that it was already discovered 47 years ago by David Kulish. And so, but I'm just going to give a rather different way of thinking about some very old work and tying this all together. But I think a more physical way of thinking about it, and that physical way of thinking about it is going to motivate three conjectures, which I'll make, one on quantum electrodynamics, one on non-abelian gauge theory, and one on black hole information. So let me give here a lightning overview of some of the recent discussions in quantum electrodynamics. Now, you're all familiar with the statement that in a abelian gauge theory, the global charge is always conserved. The sum of the incoming charges is equal to the sum of the outgoing charges. But what has been more recently understood that this is only one in an infinite family of conserved charges. And let me describe what these conserved charges are. And this is going to be a quick review of something which sometimes people lectures on. So here's a picture of Minkowski space. In the future, at null infinity, we'll use retarded time u, advanced time at past null infinity v, and the celestial sphere at null infinity, we'll use the coordinates z and z bar, and here is square plus, where light rays go to, square minus, where they come from, and we'll also be interested in the past of square plus, which is not square plus minus, and that has to be carefully distinguished from the future of square minus, which we call square minus plus. And the statement is that if we look at the radial component of the electric field on the sphere at the bottom of square plus, that is equal to, antipally, it's not equal to the same point, it's antipally equal to the radial component of the electric field at the future of square minus. And this can be thought of really as a boundary condition which defines the scattering problem, which is needed to define the scattering problem in Minkowski space. And this integral, for instance, I found a little bit funny. I'm not going to have a long discussion of it now, but it's implicit in every problem in Jessen and every quantum field theory computation. It would not be a Lorentz invariant without this integral identification. And which undoubtedly in some form known to Maxwell and Leonard and Wiener. Now this looks a little bit trivial, but it suddenly starts to look, this by the way is one identity for every point on the sphere, and it's a conservation law. It's an incoming thing that equals an outgoing thing in any scattering process. It starts to look more non-trivial if we integrate by parts and along a null generator of square plus, and then we can write this charge and use the constraints to integrate by parts. We can write it as the integral along the generator of square plus of the divergence of the radiative component of the electromagnetic field plus whatever hard charge is, like we can imagine here that we could have massless charged particles which go through square plus. And in fact, in all of this talk, just to simplify things, I'm going to assume that all charges go through square plus. We can also consider massive particles that go through time-like infinity, but there's a beautiful story there, but it's substantially linked to the discussion. So I'm just going to talk about charges going through null infinity. Now, the so-called soft charge, if we work in AU equals 0 gauge, is the total U derivative, and it's related to the shift in AZ, which if space is flat, if the magnetic field vanishes in the far past and the far future, this soft charge measures the shift in the flat connection on the sphere of infinity, and these in turn label degenerate vacuum in abelian gauge theory. So the soft charge is related to the shift in degenerate vacuum, which is the electromagnetic analog of the memory effect that we just heard Gary describe a few minutes ago. And there's a similar story on square minus. And the statement that Q plus equals Q minus is not only true in classical electromagnetism, but it's an exact statement in any quantum theory with an abelian gauge symmetry, and it's known as the soft photon theory. Okay, so that's a lightning review of that. Now let's apply our knowledge of this conservation law. And let's apply it to something insanely simple, which is Higgs-Boson scattering, E plus E minus goes to E plus E minus. There's a together H there. Now, of course, we can't just have electrons, again, I'm making them massless, and positrons going to infinity, because we have to solve the Maxwell constraint equations. And we're assuming that there are no incoming radiative modes, no photons. So here I've written the constraint equation on square plus, and there's no incoming radiative modes. So I'm setting these modes to 0. And so the constraint equation tells me that the U derivative of the radial component of the electric field on square plus must equal the flux of the charge current through square plus. So now if we set the fields, the Coulomb field to 0 up here and down here, and we integrate, we'll find that we'll get some non-zero radial electric field here and here. And similarly, setting 0 here, we'll get non-zero here and here, but they will not antiqually match unless the scattering is trivial. If the scattering is trivial, the total scattering antiqually match, and everything is okay. And so since they don't obey this matching condition, Raman scattering is identical to 0. The quantum amplitude to scatter an electron or positron and get out an electron or positron is identical to 0. That is implied by this conservation law. Now, in fact, this result has been known for a long time, but it's stated in a rather different way. And here's how it's usually stated. Photons between external lamps. And these diagrams have infrared divergences in them. And they're become infrared divergence when the energy of this photon becomes very low. And in quantum field theory, anything with very low or zero energy is called soft. So when this photon becomes soft, this loop integral of the momentum around here diverges. And this diagram is actually infinite. But that's not the end of the story. There's a next diagram with infinity squared. And this has been analyzed in a very rigorous way. That's what Pinocchio number famously proved. One of the things they famously proved. And you add the whole thing up, and you get e to the minus infinity, which is 0. So what I want to say here is that these infrared divergences is just the penalty that quantum field theory extracts on us if we try to compute something whose amplitude, we try to compute something that is violating the conservation law. So I would say there are no real infrared divergences in quantum electrodynamics. They are just there to set things to 0 that we shouldn't, when we try to compute something we shouldn't have been computing in the first place. Now, it's not very impressive just to compute 0. We want to compute something non-zero. We know something is non-zero. So what could be non-zero? So the problem was that we had these Coulomb fields that were going down to the bottom of square minus and the top of square plus, and they weren't matching. So let's field them. And in fact, let's solve the constraint equation not using the Coulomb field at all, but let's solve it using the radiative piece. Of course, there are many things you could do in between. You could have some Coulomb piece and some radiative piece, but I'm discussing the other extreme where there's only a radiative piece. So the radiative solution of this equation, I'm imagining that I have a particle that comes out to square plus every time on u0 at the point z0 on the sphere. I can solve this equation for the radiative field az, and a number of interesting features of it. One is, eccentric u equals u0. It's pure gauge. And it has a step function in it. So there's a shift. It's a different pure gauge at plus infinity than it is at minus infinity. That's the vacuum shift I was talking about. And moreover, if we take its Fourier transform in retarded time, we get a pole. We get a soft pole as omega goes to 0. Now, we can also, this is a classical solution of the constraint equation, but we can also make a dressed coherent state, which is annihilated by the constraint equation without adding the Coulomb. The Coulomb field. Now, of course, we can't shield the 0 mode of the Coulomb field with photons. But we've got E plus E minus here, so the net charge is 0. And when the net charge is 0, there are long-range 1 over r squared terms in E that are not spherically symmetric. And what we would be doing here is shielding, so since the whole state is neutral, we can't shield the entire Coulomb field. And then the matching condition is trivially satisfied. And since the matching condition is trivially satisfied, there's no reason the amplitude should vanish. And indeed, it's known that the scattering of these dress states that I just wrote down is in fact infrared finite. And this was shown in a way that is rather hard to see that's equivalent to what I just said, because the language that is used in 1970 and so on, and not talking about 1930, the language that's used is very different. But Tadeusz Coolidge wrote down some dress states that have the property that the long-range Coulomb field is shielded, and showed, and the proof was improved over the years, and there was also Charlie Pibble, they showed that scattering amplitudes of these states are infrared finite. And what happens is, this exchange, every particle now is surrounded by a Coulomb cloud, and the exchange diagram between external charge particles, which has infrared divergence, is canceled by an exchange diagram in which the external changes the soft photon of the cloud of the same particle. And that cancellation is possible because this cloud has an explicit pole as omega goes to 0. Okay, so there are these obscure but somewhat studied infrared finite scattering states, and what we've constructed is equivalent from those, so we don't have to do a lot of hard work to show that this gives us something which is infrared finite. Now, one thing I want to say here is that these clouds don't really, I mean, I've drawn it in this way, but they don't really surround the asymptotic hard particle. Indeed, if it's a massive particle like an electron, that will go to time-like infinity, whereas the soft photons will disperse out to null infinity. Okay, so what I've done is just recovered from a modern viewpoint a way of thinking about infrared divergences and thinking about how you actually can have an S matrix in quantum electrodynamics, despite the appearances of infrared divergences at intermediate stages in the calculation. Now let me go on to the conjectures. So, Fedaya-Coolidge states, not all states are Fedaya-Coolidge states. In fact, Fedaya-Coolidge states are highly unphysical. When we do an experiment at the LHC, we do not scatter Fedaya-Coolidge states. In order to do that, every time we set in a pair of photons, we would have to follow it up by a cloud of radiative photons whose distribution was tuned in just such a way as to cancel the long-range Coulomb field. Obviously, we never do that. So, however, so the conjecture is that you can move the cloud from the incoming state, the soft cloud from the incoming state to the outgoing state, and one can show, I won't go through the discussion, that if you move the cloud in the right way, that this cancellation of infinities has a very natural interpretation as just the soft particles. We take a bunch of undressed charged particles and we scatter them, and there's a bunch of soft particles that the conservation law forces us to produce in the scattering process. And we've actually, this conjecture is actually rather easy to verify for the leading infrared divergences to get into the details of the multi-loop diagrams and make sure there's no subdivergence. Some diagram will be some work, but I think that should be doable. Okay, what about non-abelian gauge theory? Non-abelian gauge theory, there is no analog of the Fedaya-Coolidge proposal. The intricacies of the non-abelian structure in non-abelian gauge theory have the Fedaya-Coolidge arrived at their state in a way that it would now seem extremely indirect, and it was too hard to follow their steps for the non-abelian